Hello class, welcome back. Today we're going to go ahead and continue our homework H, right? We're going to go ahead and continue homework H. In this section, we're going to be dealing with, in this homework, we're going to be dealing with section 4.7, applied optimization problems, and section 4.10, antiderivatives, all right? So for 4.7, I've linked a few videos and notes. All right, so 4.7 isn't going to be a lengthy video here. All right, but for each question in that section, there is a video linked and notes as well. So please watch those. All right, please watch those. Going to go ahead and go over a few of them, right? Specifically two of them in that section. All right, something that you may end up seeing for your exam 3, all right, which would be approximately, all right, in a few days, all right. So you have a question, all right. The question states, if 2100 square centimeters, all right, of material is available to make a box with a square base and an open top, find the largest possible volume of the box, all right. One thing here that is given, all right, one thing you always want to go ahead and notate is it was given to you, correct? So I was told here that 2100 square centimeters or centimeter squares. All right, we know that whenever a unit is just a unit, this is length. All right, if you have a unit square, this is volume. I'm sorry, this is area. And whenever you have a unit cubed, right, this is volume. All right, so what they gave me here, all right, this is an area, all right, this is an area. All right, so area of 2100, all right. Specifically surface area, all right, an area covering in more than one surface, right, covering the entire surface of the box. And I know that this box has a square base, right? So in other words, my box looks, that's terrible, something like that. And it's something like an Amazon box, right? All right, so if we look at that, right, I have a base, right? It's a base, all right. So its length, it's the length would be the same thing as its width, right? So it's the same unit, meaning that this would be, let's just say, base times base. You may end up using x times x, right, or whichever you feel comfortable, right? I just know it's one side times another side, right? Plus, I know that I have, not only do I have the same base again, right? Let's just say of unit x, and it's gonna be, right, and if I want to look at the face of this, right, of this side of the box, it is that base times this height, right? And let's just say this height would, let's call it y, right? Times y. So, and how many faces of these do I have in this box, right? How many faces of those do I have? I have 4 of them, right? So in other words, and I'm not going to do anything with the top because it's an open top box. Right, so I'm not looking for that surface area, right? Meaning that my surface area would be x squared plus 4xy, all right? Or you may even use this one up here, all right? I also know the volume, right, of a box. It's length times width times height, right? If we're dealing with a cubed, right, or for this case, right, it is base times height, all right? Or you may even be looking at x squared times y, all right? That's actually what I'm going to want to be dealing with these in terms of x and y, right? In terms of x and y. And so in other words, I have these two formulas. And whenever it comes to these problems, right, these optimization problems, you want to get two formulas that you are familiar with, that you're familiar with, right? Using units that you're aware of, right? So in other words, they give me the surface area of a box. So that's right. That's the formula I want to go ahead and use. I also knew that I wanted to use volume because that's what was being asked. All right. So I'm going to be working with these two. All right. where I need to go ahead and optimize this problem, right? I need to go ahead and optimize this problem. And generally, whenever you're solving these, you of course, right? We're going to go ahead and derive, but we need to go ahead and get everything the same unit, right? I need to get everything in terms of x or everything in terms of y, all right? So for this specific problem here, let's see. So I know my volume is equal to x squared times y, and I know that my surface area for this box is x squared plus y. I'm told that I know what my surface area is. That's 2100. Equal to x squared plus 4xy. All right. I need to go ahead and find the maxima, right? The max possible volume of the box, right? And this is going to go back to those functions we were doing before under previous sections, right? Finding the max point or the min point, right, by taking the first derivative test, right? And this is exactly what we're going to go ahead and do now. So I'm going to want to go ahead and derive my volume function. But I have two variables. I have an x squared and a y. I don't want the y there. I want to derive everything with respect to x, right? And this is where you're going to go ahead and compare it with your other formula, right? You can get you know what y is with your other formula, all right? So in other words, you're going to get the surface area and you're going to solve for y. I'm going to go ahead and subtract x squared from here. I'm going to get 2100 minus x squared is equal to 4xy, right? And therefore, y is equal to 2100, all right, minus x squared over 4x, all right? I'm going to go ahead and plug that into my volume formula, right? This here is going to be if volume is equal to x squared times y, and you know what y is, all right? Y is just 2100 minus x squared over x. I can go ahead and work with that instead, right? I can go ahead and find the maximum volume, right, of this function, right? I can find the maximum or minima. All right. So this here ends up, I cancel this out with one of these, leaving me with x times 2100 x squared. Therefore, this is v is equal to 2100 x minus x cubed. All right. Very nice. Awesome. All right, what do I want to go ahead and do now? I want to go ahead and derive this function, right? Meaning this is 2100 minus 2, oh, almost, minus 3x squared, all right? We stated whenever we want to find the maxima or minima of a function, we equal the derivative to 0, meaning I have 2100 minus 3x squared is equal to 0, and I'm going to go ahead and solve for x. All right, you shift things around, you get 3x squared is equal to 2100. You divide by 3, all right? This should give me 700, meaning you're going to go ahead and take the square root, all right? Go ahead and get that calculator. Right, so this here gives me the square root of 700, right? Which is just what? The square root of 100, square root of 7, which is 10 square root of 7, which, right, if you wanted to go ahead and find the decimal to this, right, this is 10 square root of 7. Right, this is approximately 26 point, what do two decimal places? 26.46. All right, 26.46. Oh, we're worried about units too, right? So these are centimeters. Right, this is just the distance, centimeters. Right, so this is the base of that box, right? It's 26.46 centimeters. You can find the height of the box, right? Because you found a formula for this, right? Which was, you stated y is equal to 2100 minus x squared over 4x. All right, so let's go ahead and plug that in. You get 2100 minus right? And we should get, I got that height to be approximately 13.23. Let me go ahead and check that again one more time. 2100 minus, that cancels out. That over, or times that. Yep, that's what I got, 13.23, right, centimeters. All right, so this here ends up, but those are my dimensions, meaning, all right, if I go plug everything back to the volume function, right, this should be squared 13.23. This should be approximately what? This here give me approximately 9261, where we're dealing with volume. So this here is going to give me a centimeters cubed, right? So there we go, all right? Let's just say you want it to be more specific, right? And I wanted you to show me by using a test that this is a maxima, all right? Well, you know your first derivative is 2100 minus 3x squared, and we know if we take the second derivative, it's inconclusive, right? It didn't end up working out for this one, but we know, right? If it was a negative, it'll mean it was my maxima, and if it was a positive, it'll state that it was my minima. All right, so inconclusive here, right? But the good thing is that it's stated in the question, right, to find the largest possible volume, right? So that is how you go. So yes, this here's my final answer. I have another one, all right? A baseball team plays in a stadium that holds 46,000 spectators. With the ticket price at $9, the average attendance has been 20,000. When the price dropped to $6, the average attendance rose to 23,000. Assume that the attendance is linearly related to ticket price, right? And the question here I want to go ahead and ask is, what ticket price would max my revenue? Real world life problems, right? So I've gone ahead and set up the data given to me as points, right? So I'm told that for whenever I got $9, my attendance is 20,000. Whenever my ticket is $6, it is 23,000, and I assume, right, that the attendance is linearly related to ticket price, right? So the first thing you want to go ahead and do is find the equation of the line, all right, which states the first thing you want to go ahead and do is find slope, right? So this here ends up being 23,000 minus 20,000 over 6 minus 9. All right, that ends up giving me, I wrote these, I have these notes for you all. All right, 3,000 over -3, all right? Very nice, right? So this here ends up giving me my slope, right? So this here ends up giving me my slope. All right, so to find the equation of the line, we know that is y minus y1 is equal to m x minus x1, all right? Where, so it's going to be y minus 20,000 is equal to negative 1,000 x minus 9, all right? So my linear function will then be all right, adding 2,000 to both sides. Therefore, my function is, my y function is equal to negative 1,000x plus 11,000, all right? what I have here is now is a quantity. All right, this is my quantity equation. All right, what I need to go ahead and now do for step 2 is find my revenue function. All right, that simply just states that I'm going to multiply everything that I got by the price, where the price is X. So I'm going to multiply it by 1,000 by X, right? Right, in your book, you may see it as, or in other questions, you may see it as X times P, where P, right, is the quantity. All right, and you're multiplying that by X. All right, so here I'm going to get my revenue function to be negative 1,000x squared plus 1,000x. All right. And of course, right, I'm looking for a maxima or a minima. All right, I'm looking for a maxima or minima. So I'm going to go ahead and take the first derivative. It's 11,000. All right. And again, what am I going to do? All right, I'm going to go ahead and find the equalist to 0. All right. I'm going to go ahead and equal this to 0. So meaning this here would end up giving me 0 is equal to -2 plus. All right, I'm going to go ahead and solve for x. All right. All right, so give me 1 second here. All right, meaning I'm going to subtract by that, meaning you got -2,000x is equal to -1,000. All right. I'm going to go ahead and divide both sides by -2,000. This gives me these cancel out, these cancel out, these cancel out, leaving me with 11/2, which is approximately, right, 5.5 or $5.50, right? So that price right there would maximize my revenue. Very, very, very nice. All right, so this leads us to section 4.10, right? Perhaps one of my favorite sections moving on forward, all right? We're going to get introduced to antiderivatives. All right, you're going to get right. And the reason we use the word antiderivative is to give you an idea of what is going on, right? We're going the other way now, right? Instead of deriving a function, we're going to take the antiderivative, which is also known as integration, right? We're going to go ahead and integrate, all right? So we're taking things backwards, and it's a really beautiful concept, right? Some really beautiful rules that go on here, and it's hopefully you find the beauty in it, right? Why it's used. The majority of calculus 2 is based on integration, all right? And I would probably state that it's probably one of the best most used math courses, right? Calculus 2. It's such a wonderful course. So, and if you're using your cheat sheet, the one that I had provided, you'd notice that this is the right-hand side now, right, of the page. This is the right-hand side. Right, so even though the word antiderivative is used, I'm going to just jump straight into it and state the integration. That's what I'm going to be stating, right, integration. All right, so we know, all right, for example, we know, let's go ahead and do, yeah, you know what, let's do a good example. All right, so I have a function here. All right. I have this function here, plus 7. All right. I have this function here. I want to go ahead and derive this. All right. So the main function was capital F. I'm stating I'm deriving it by just lowercase f. So this here would be 6x, and the derivative of a constant is 0, right? So there, boom, there we go, right? This is the derivative of that. But now I need to go backwards, right? I need to go backwards. The rule we're going to be learning here is known as the power rule. Whenever you're integrating variables, right, functions, you know, with a power, right, with a degree. So what you start here, all right, you'd see is this sign here is an integration sign. I need to integrate 6x. And at the end of all these integrals, you're going to write dx, right? Dx states that, hey, this function was once derived, right? And I need to integrate it with respect to that variable. All right, as we proceed with the class, you'd see, right, you can integrate with respect to different variables. And what happens whenever the variable you're not integrating with respect to is involved, right? So the rule here is you're going to get the exponent, you're going to add it plus 1, and then you're going to divide by the new exponent. All right, so in other words, for this function, this is 6x raised to the 1 plus 1 divided by 1 plus 1. All right, this here ends up giving me 6x squared over 2, which is 3x squared. And hey, look at this. That is exactly that. How freaking awesome is that, right? How cool is that? But you may be saying, hey, what happens to the 7? Is there any way I can ever retrieve that 7? No, there isn't, right? Because as soon as you derive it, it goes to 0. All right. I don't know if you had a 7 there. I wouldn't know if you had a -5 or 1,000 or 3 over 4. A constant goes to 0. That is why whenever you're integrating and you are not given any bounds, generally you're going to be giving a number here and a number there. But right now, we're not. I'm not going to give you any of those. These are called as indefinite integrals. It's not defined, right? It's indefinite. It's not defined. It's just a regular integral. And it's very, very, very important that whenever you're integrating these, you write plus c at the end whenever it's an indefinite integral, right? To state that, hey, there could have been a constant here, right? There could have been a constant here, right? If I'm mirroring these two, I knew that my constant would be 7. All right. You may also state, hey, what if I didn't have any 7 there? What if it was just a 0? Well, that would, right? What if there was nothing there? Well, there's never really nothing, right? There's technically, you can always add something, right? It'll be a plus 0, meaning your constant was a 0. Right? Okay, let's go ahead and move forward. I'm going to do a few of these, right? This is going to be a long function, all right? This is going to be a large function, and I'm going to break this piece by piece, all right? So this states that, hey, this was once derived, right? And I need to go ahead and get the original function. Okay, so what I'm going to go ahead and do is I'm going to take the integral of all of these. I'm integrating with respect to which variable? X, right? Because this was once derived by x, right? So I'm going to write dx at the end. All right. The great thing about integration, right, is that you can apply if things are separated by a plus or minus, all right. If terms are separated by plus or minus, you can apply to each one of these individually. All right. So in other words, you now have the integral of 9x squared plus the dx times dx plus the integral of 3x dx, right, plus the integral of -2x to the 1/2 dx plus the integral of x to the -3 over 4 dx plus the integral of -7 dx. Right, and if you notice here, I have different scenarios, right? I have different scenarios. Let's go ahead and do this one first. 9x squared. Okay, so the point of the game is, right, you add 1 to the top, so it now becomes a 3, and you're going to divide it by the new value. All right, that is my integral, and I can simplify this, meaning this is going to be 3x cubed. Right, I don't need to write a plus c, I just need to write it once. All right, You don't have to do it for each one like these, right? I can write it to the very end. So this here is my integral, right, for that one. Plus, let's go ahead and move to this one, right? One great thing that you can do whenever you're integrating coefficients, like the one right here, you can factor them out. So technically, this is just 3 times the integral of x dx. And you're going to find its benefits. You're going to go ahead and see the benefit in that, right? The gain here is 1, right? Whenever there's nothing up there, there's a 1. Right, so this is going to be 1 plus 1. This is 2 divided by 2. And don't forget to bring down this, right? To bring down that. So in other words, that is your integral, right? Your integral for this function, let's go ahead and make that a little bit lower, is 3x squared over 2. Okay, very nice. Let's go ahead and do this one here. There's a negative. I don't want that, right? So let me factor that out. This is a negative 2 integral of x to the 1/2 dx. And just like before, right? I'm going to show you 2 ways to do this, all right? So I'm going to add the top by 1, right? By 1. That is the same thing as, right, 1 plus 1 is the same thing as 1 over 2 plus 2 over 2, which is 3 over 2, all right? So this means that my integral would be negative 2 x to the 3 over 2 divided by 3 over 2, all right? Oh, you need to go ahead and simplify this a little bit more. I do not want this in the denominator, so I'm going to multiply the top and the bottom by its reciprocal by 2 over 3, the top one by 2 over 3, meaning I get negative 4 over 3 x to the 3 over 2, right? Meaning, well, prior meaning, I think I'm going to have to move this one even a little bit lower now, right? Right, so that's what it gave me, right? This canceled out with this. Negative 2 times 2 is negative 4 over 3. Very nice, right? So this here gives me negative 4 over 3 x to the 3 over 2. And you might be saying, hey, am I going to have to do that all the time with that? You know, even dividing by a fraction? No, there's an easier way, right? The method that I like. You may take that route first, right, to get your feet wet. But eventually, you're going to want to go straight, perhaps, to this method, right? So again, and I'm taking the integral of that. So this is going to be x to the negative 3 over 4. And we said, right, adding by 1 is just the same thing as adding by 4 over 4, right? So this here is going to be 1 over 4, all right? We know that dividing by a number is the same thing as multiplying by its reciprocal, right? Over 1, right, which is just 4. So that's what you want to do here now, right? This is what you want to do with these fractions, right? So instead of dividing by 1 over 4, I'm just going to multiply by 4. Hey, that's much nicer, right? So what I have here, right, ends up being 4x to the 1 over 4. Sure, you can take the other route, right? You can do 4x to the 1 over 4 over 1 over 4. I'm sorry, x to the 1 over 4 over 1 over 4, and you find out it gives you the same answer. All right, so then here this is plus 4x to the 1 over 4, right? And then we have a constant, right? The derivative of a constant, all right? Whenever you have just this regular constant, this regular coefficient, all right, just there by itself, right? Sure, one way you can look at it is you can factor out that negative 7. Negative 7 integral of dx, all right? All right, what do you think is go there? What do you think is going to go there? This here is going to be negative 7 times x. Why? What happens whenever you take the derivative of something like this? The x goes away, right? Because you're dealing with the power of 1, right? The x goes away, right? So the derivative is that, meaning that if you wanted to go backwards, you just attach the x, right? Another way to look at this is what you have here, right, is the integral of negative 7 times x to the 0. All right, because what is x to the 0? Anything to the 0 is 1, all right? Meaning if you were integrating this, right? This is, all right, let me factor out that -7. This is -7. X to the 0 times dx, all right? By following those rules, this is -7, x raised to the 0 plus 1 over 0 plus 1, all right? So this is -7x to the 1 over 1, which is just -7x, all right? Just remember, whenever you're integrating a regular coefficient, right, just attach an x to it, right? And at the very end, I'm going to add plus c. So you right there, the mathematician, just found the integral to this derived function, right? And if you don't believe me, right, you can go ahead and take the derivative of all of these and find out it's going to give you exactly those up there, all right? Okay. Trig functions, right? Trig functions. There may be some confusing with these. It's not confusing, right? It's just, remember, right? If it helps you initially, because I remember as a student a few years ago, right? I would do this, right? Whenever I would derive, I would go this way. I got sine of x. The derivative of sine of x gives me cosine of x. The derivative of cosine of x is negative sine of x, right? Because it changes. The derivative of negative sine of x is negative cosine of x. The derivative of negative cosine of x goes back to the beginning, right? It's sine of x. It repeats, all right? So that means if you wanted to go backwards, you would have to go the other way around, right? You would have to find the integral, right? You would find the integral going that way. So, all right, here, let me go ahead and factor out this -4. So this is going to be -4 integral of sine dx, meaning I can just find the derivative of sine of x, right? And then I can just multiply by -4. All right. So in other words, one way to think about this as well is whenever the derivative of what gives you sine of x, right? Whenever you derive what, it gives you sine of x. Which function is that? Oh, okay, you're the mathematician, so you know, hey, I know cosine gives me sine, but it's cosine changes sign, so that means it has to be negative cosine, because the derivative of negative cosine gives you positive sine, all right? So the derivative of this would be negative cosine of x plus c, right? Right, and if you, of course, right, you don't believe me, right? You can go to sine here and find out, wait, what gave you sine? Well, if you go back to the bottom, that's negative cosine, right? If you were to derive negative cosine, it gives you sine, all right? And here I would distribute, so that means the derivative is, the integral is positive 4 cosine of x. And again, right, you can test this out, derive this, right? Take the derivative of this. If I say, hey, this is my function y, meaning y prime would be 4 times negative sine of x, the derivative of a constant is 0, meaning y prime would just be -4 sine of x. Hey, awesome. This is exactly what was given. Right. Here's another one, right? Again, another one. And the great thing here is that you can factor out negative values by themselves, right? Certainly there's a coefficient there to 1, right? But this is just negative integral of cosine of x dx, right? And the derivative of what gives you cosine? Oh, that's just regular sine, right? Regular sine. And make sure always sure you're going the right way, right? Because I remember myself and just just teaching the class. It's always I know for the first part of the class we're used to dealing with derivatives going forward, but don't forget we're going backwards now, right? We're going backwards, right? So put the car in reverse, right? So this here would be sine of x plus c, meaning my integral sine of x plus c, negative sine of x plus c. Right, remember, we're going in reverse now. We're going in reverse. All right, here's another one, right? You have the integral of 1 over square root of 1 minus r squared times dr. Times dr, times, right, times the derivative of r, right? So this just says, hey, you're just dealing with a different variable. You need to integrate this. All right, and these are one of those identities that you just have to know, right? You may be looking at this, you're like, hey, this looks pretty familiar. Yeah, it is, right? This is one that we should know, right? This here is inverse sine, right? This would just be inverse sine of r plus c, right? Sure, you may see it as arc sine as well, right? So you may even see it like this, arc sine of either one of those would work, right? Arc sine. Very, very, very nice. Okay, let's step it up here, right? I'm told I have a function. All right. Let big F be the antiderivative of little f, right? Meaning that I need to integrate. And I know that whenever I do integrate, whenever t is 0, f is 0, all right? Because what I have here is f of t equals something, right? The middle value is 0, so right, this is saying when t equals 0, big F is going to equal 0, right? Big F equals 0 is stated by that 0 over there. All right. So in other words, I'm going to go ahead and integrate this. Let's integrate this function. All right. 3 secant squared of t minus 10t cubed. And I'm integrating with respect to the variable t. All right. So let's go ahead and see what we can do. All right. I'm going to go ahead and apply this integral to each one of those. All right. I can do integral of 3 secant squared of t dt plus integral of negative 10t cubed dt. All right. This one would be secant squared of dt minus 10 integral of t cubed dt. All right. The derivative of what gives you secant squared? The derivative of what gives you secant squared, right? You remember, right? So ones that we should have memorized. These are ones that we should have memorized. You find out that this is tangent. All right. Minus 10, applying the power rule, that is t, 3 plus 1 is 4, divided by 4 plus c. All right. And I said that if I were to integrate this, this would be big T. All right. So let me go ahead and polish this up. This is f of t is equal to 3 tangent of t minus 10 over 4. That's 5 over 2 t fourth plus c. All right. Here, what they gave me in the beginning were known as initial conditions. All right. These are known as initial conditions. What's inside there is my t value. So they're saying, hey, f of t equals 0 whenever t equals 0, right? And the reason they do that, it's because they want you to define c. They want you to find out what c is, all right? So I'm going to go ahead and plug in what they gave me, all right? So you're going to want to save this one, right? This is an OG. This is an original one. You're going to want to save that because once you find c, you're going to plug it back into there. All right, so they're saying f of t equals 0 whenever t is 0. Right. So it gives me that right there. Sorry about that. Right, what is tangent of 0? Right, what is tangent of 0? 0, right? Because that's sine of 0 over cosine of 0, right? And sine of 0 is 0, so that's 0 divided by 1, which is a 0. So 0 equals 0. 0 to the fourth is 0. 0 times 5 over 2 is 0. So that means that entire part is 0 plus c. So in other words, it's 0 minus 0 plus c. So in other words, right, c is just nothing. It's 0. Right, meaning your final answer, right, with the initial conditions applied would just be f of t is equal to 3 tangent of t minus 5 over 2 t to the fourth plus 0, or in other words, f of t is 3 tangent of t minus 5 over 2 t to the fourth. That there would be your final answer, right, with c already involved, solved for because due to initial conditions. Your initial conditions may be given like this, where they're saying, hey, you're giving something, this is the second derivative of something. They're giving me initial condition stating that for the first derivative is equal to negative 3 whenever x is negative 2, and the function itself is equal to 1 whenever x equals negative 2. All right, so I'm going to want to go ahead and apply that, right? I want to go ahead and apply that. All right, so this is my derivative. If I integrate this, right? If I integrate this, this is going to be just the first derivative, meaning I can apply the power rule here, right? So this is going to be 7x to the 2 over 2 plus 2x plus c. All right, if you need to go ahead and pause the video, please do so, okay? And to make sure that you fully understand that, right? So this is the formula for my first derivative, all right? And I was giving initial conditions. My initial condition stated the first derivative is equal to -3 when x is equal to -2, all right? So I'm going to go ahead and plug that in, right? So this is f of -2 is equal to 7 over 2 to -2, right? Every x is -2. And why do I want to do this? Why do I want to do this? Because I want to solve for c, right? I need to solve for c. And if you're taking, if you're an engineer, right, you're definitely going to be seeing initial conditions in your functions, specifically whenever you get to differential equations, which is another beautiful class, right? Which just it's heavily based on your Cal 2, all right? So, right, you may want to take extra notes here, all right? That's another great class, differential equations. If you have the option to take it, and if it's not part of your major, please take it, right? It's a wonderful class. I went off on a tangent again. My apologies. This is 7 over 2 times 4 minus 4 plus c. And I know what f of -2 is, right? That was given to me. That's -3. So this is -3 is equal to 7 times 2 minus 4 plus c, right? I'm just kind of skimming through these parts because this parts, right, parts like these you should know how to do by now. And if not, just pause the video, all right? Pause the video. Take your time, right? Take your time. As long as you take your time, that's fine. Right, so I get c is equal to -13, right? By just algebraic manipulation, right? 7 times 2 is 14. 14 minus 4 is 10. -3 minus 10 is equal to -13, right? So, and just like before, the one that I wanted to save was this one here, the one that I derived. All right, that one. So meaning that my first derivative with c already solved is 7 over 2 x2 squared plus 2x plus c, but I know what c is -13. And I'm not done yet, right? I'm not done yet. I need to find the original function. So let me go ahead and integrate this, right? When I integrate this, hey, I get back to the original function. This is 7 over 2 x to the third over 3 plus 2x squared over 2 minus 13x plus c. All right, let me go ahead and polish this up. All right, this here ends up giving me 7x to the third over 6 x squared minus 13x plus c. All right. I was giving another initial condition for this function. I was told that my initial condition was whenever the function at x equals -2, it is equal to 1. All right. So in other words, I'm going to replace anything with an x with -2. All right. So f of -2 is equal to 7 -2 to the third over 6. And whenever you're doing these, please stay away from decimals, all right? You definitely need fractions here. Do not round to your decimal. Do not round to decimals, right? You will get points deducted for that. Wow, right? And I know what f of -2 is, right? I've told you that f of -2 equals 1. So this is 1 over 7 times, what is that? -8 over 6 plus 4 plus 26 plus c. All right, so this is here is -7 times what this ends up simplifying, what, 4 over 3. So 7 times 4 over 3 plus 30 plus c. So this is 1 minus equals -28 over 3 plus 30 plus c. Let me move that -30. Let me move this one. Move that one over. Whew, all right. This is negative 29 is equal to negative 28 over 3 plus c. Add 28 to both sides. Add 28 over 3 to both sides, meaning negative 29 plus 28 over 3 is equal to c. I need to have these have the same denominator, so I'm going to multiply that by 3, multiply that by 3. 30 times 3 gives me 90. 90 minus 3 gives me what, 87? So this is 87 over 3 plus negative 87 over 3 plus 28 over 3 is equal to c. And at this point, I do need my calculator here. Negative 87 plus 28, right? This gives me negative 59 over. Wow, right. One thing you will notice as well as whenever you get to integration or just calculus-based courses is the majority of the points isn't taken off for, at least in my experience, right? At least in my experience, the majority of the points are taken off for computational algebraic steps, not for the calculus-based stuff, right? You'll see the students, they rock it, you know, they get the integration and the derivatives, and they know those. It's just when it comes to applying the algebra, that's where the majority of points are honestly taken off. It's where I've seen as an instructor, and where my points would be taken off, right? Would be like, oh, I forgot that negative in the, you know, like 2 rows above, you know what I mean? And you know, with algebra, right? What if one negative value is off, the entire thing is going to be incorrect, right? And this is another reason why I asked, show me all your work, right? Show me all your work, because if you just give me the answer, first of all, you need to prove it, and I won't be able to give you any points. So unfortunately, I would have to give you negative 10 points, right? In other words, I would give you 0 points. But if you showed me all your work and I see where you went off, right, where you might have gone off, hey, I give you partial credit for that, all right? And partial credit is better than no credit, all right? The function, again, on the tangent, what is this, calculus, right? The function I had was right there, and I solved for c, meaning that my f of x function is, oh, actually not, it's the one in the bottom, that's much nicer. It's a 7 over 6 x to the third plus x squared minus 13x minus 59 over 3. Whoa, right? If you were to go ahead and derive this twice for fun, if you got extra time, you'd find out it gives you the exactly same thing that you were given, the second derivative. All right, you have another one like these, right? I'm not going to go ahead and solve this one for you. I'm going to go ahead and set it up for you, right? Right, so you have this function, and they need you to integrate it, right? Just like before, there's one thing that I need you to do, right? And you need to be careful with these signs, right? This here can be rewritten as 5x to the negative 3 minus 5x to the negative 5, all right? Right, so pretty much what you can do here is, right, if you're going to go ahead and integrate this, right? The integral is the capital F, right? So this is going to be 5x to the negative 3 plus 1, all right? Again, you're going to the right, right? If you need to use your calculator for this, please use it, all right? It is right there, right? It is right in front of you, right? Negative 3 plus 1 does not give me negative 4. That gives me negative 2, all right? So this here would be 5x to the negative 2 over negative 2, right? The one on the right would give me negative 5x to the negative 5 plus 1. That gives me negative 4, x to the negative 4 over negative 4. Meaning after you simplify it, right, this should give you 5x to the negative 2 over negative 2 plus 5x to the negative 4 over 4, right? X raised to the negative 2, right? You know what that is, right? Again, right, you would have to simplify those, right? X raised, right? So this here would give you 5 over negative 2 x squared plus 5 over 4x to the 4th. Oh, and don't forget plus c, right? Oof, almost forgot, right? Almost forgot. Very, very, very nice. right? And then you would just have to plug in those initial conditions to solve for your C, right? And no, just because there's a 1 or 0 for initial conditions is going to guarantee that your C is always 0, right? You need to go ahead and show your work. Right, we're going to go ahead and be dealing with some physics problems. All right, a few of you that are in this class, you do have to take university physics. All right, what we're about to go over here is something you cover in University Physics 1. All right, so let's go ahead and get started. You are told that a ball is shot from the ground straight up into the air with an initial velocity of 4,747 or 4,747 feet per second. All right, so right, but you're looking at this formula, right? We're looking at this formula. This here is going to go ahead and this here is going to be my final position. This here with an I is my initial condition, my initial position. This here is going to be my initial velocity. This is my time function, right? And this here is acceleration, or the constant gravity, right? The gravity constant, right? Which is always given, right? That's always going to be given. If it's not given, you assume it's depending on the units. If it's meters per second squared, is going to be 9.8. But here we're dealing with feet, and if we're dealing with feet, I'll go ahead and give you that. All right, I'd be giving you those. What am I trying? I'll give you those units. All right. So if we're dealing with feet per second, right, then I would tell you that this is 32 feet per second squared. It's if you're dealing with meters, right, this would be right. Okay, so I'm going to use this function here, this formula, right? I can find initial position. I can find the final position of pretty much anything as long as I know the initial position, the initial velocity, a time frame, right, and the acceleration constant. All right. So let's see what do I know here. All right. What do I know here? I am told here that a ball is shot from straight up into the air with initial velocity. Okay, so I know what my acceleration is, and I also know my initial velocity, right? My initial velocity is 47, right? And you actually know your initial position as well, right? If you were in the ground, right? This is feet per second. Right? If you were in the ground, if you're at base level, remember, if you're at base level, your height is 0 at that point, right? So here, this is 0 feet, right? Depending on the units we're using, right? I'm going to go ahead and plug all of this in. My final position given by my initial position, which is 0, plus my initial velocity, which is 47 t plus 1 over 2 times 32 t squared. All right, this here is given. All right, 47 t plus what's that? 16 t squared. All right, so this right here is my function. Right, this right here is my function. So this here is my position function. Right. What I want to go ahead and now write is find my velocity, right? Remember that I had stated if you have position and you were to derive this, you get velocity. If you were to derive velocity, this gives you acceleration. All right. Now the great thing about this is if you go backwards, if you have acceleration and you integrate, you're given velocity. If you have velocity and you integrate, you're given position, right? So this is going to be very, very helpful in the upcoming sections, right? So I have a position function. Let's go ahead and find velocity. All right, so let's go ahead and find that instantaneous velocity. So S prime of t is equal to 47 plus, actually, my acceleration has to be negative. All right, this here has to be negative. Acceleration function in physics is negative. squared, right? Meaning, oh wait, let me derive that one. That is the derivative of negative 16t squared is negative 32t, right? Right, and what s prime, right? One thing to remember is the derivative of s is just v, right? The second derivative of s is the first derivative of v, which is just acceleration, right? To remember that. Right? If you get to acceleration, if you're dealing with acceleration, that means your position function was derived twice, which means your velocity function was derived just once. All right. Okay, very, very nice. So meaning my velocity here is 47 minus 32t. Right, meaning I can go ahead and find that point. All right, I can go ahead and find the maximum point of that position function. All right, so this here, right, would give me 0 is equal to 47 minus 32t, or t algebraically, right, you see is 47 over 32. What's that time function, right? What's that give me? 47 divided by 32. I got, let's see here, 47, making sure I wrote down everything right. 47. So you're very nice. This here ends up giving me 148.3. 0.3, right? Very, very nice. 148.3, right? One thing that I want to go ahead and do now, right, is let's go ahead and move that over there. Awesome. Right, one thing that I want to go ahead and do now is go ahead and plug it into the original function, right? Let's go ahead and plug it into my position function. All right, so this here, right, ends up giving me, where's that function? 47 t minus 16 t squared, right? This here ends up giving me s of t, t forget, right? Plugging all that in, right? Plugging all that in. Oh, I am so sorry. I just realized that this here should not be 47. That should just be 47 feet, right? There just should be 47 feet. I'm not sure why it was doubly marked. That's why I was wondering why my information was kind of off. So this should just be 47 feet. This here should just be 47. This should be 47. This here would be 47. Wow, I'm so sorry about that, guys. This here should also just be 47, meaning 47 divided by 32 should give me 1.47. All right, 1.47. Right. So let me clear that up. I'm so sorry, guys. Plus minus 16t squared. My puppy's having a dream. Let me see. What was my time? 47 over 32. He had a rough day today. So 47 over 32. Right, 47 over 32. Yes, 47 over 32. All right. Meaning that height at that time, right, would give me, let's go ahead and plug all that in. 32 minus 16, 47 divided by 32 squared. right? I get here 34.52 feet, right? That's what I end up getting. Right. Another way you can look at this, all right? If you have this function, all right, this is a quadratic function, right? This is just y is equal to 47, right? Putting it in order, this would be negative 16x squared plus 47x, right? This is a parabolic function. It is negative, so I know it's doing this. If you want to find that max point, right, that is finding the vertex, right? How do you find the vertex of a function? If you need to find the x value, it is x is equal to negative b over 2a, right? Where b is negative, which is 47 over 2 times a, which is negative 16, which gives me 47 over 32. Oh, right. So in other words, you can use your algebraic knowledge, right? This question didn't specify how you needed to solve it, right? So you could have used the algebraic way, right? And again, right, if you have an x value, you can always find the y value that corresponds to it by plugging it in into the original equation that you're dealing with, right? Which here would have been this y function, aka the position function, right? And again, my apologies for the 4747. It was an error that was transported whenever I copy pasted. But yeah, right, and that's how you solve it with physics, right? This is how you solve it with physics. So that is my final height, right? That is my max height, 34.52 feet. All right, I have another problem here. A particle is moving with acceleration, given that, all right, I am told that at time equals 0, my position is 2. And whenever I'm dealing with velocity, my velocity at 16, all right, at time equals 0. And you want me to find the time, my position whenever time is 15 seconds, right? So this is going to go back to this, right? If you were going from left to right, that was sorry, my puppy. You're deriving, so that means if you're giving acceleration and you want to get to velocity, you need to integrate, right? You need to integrate. All right, so I have acceleration. This is 36t plus 12. Plus 12, right? So you want to integrate this, meaning this is going to become velocity, which is 36t squared over 2 plus 12t plus c, right? Meaning your velocity function is, what's that, 8? Oh. I'm not the best at 18t squared plus 12t c, right? That ends up being my function. All right. But you are given a condition. I am told that whenever time is 0, velocity is 16, right? So in other words, giving initial conditions, right? I know what v of 0 is. That is 16. So this is 16 is equal to 18 times 0, which is 0, plus 12 times 0, which is 0, plus c. Right. So in other words, c is equal to 16. And this is what I was saying. It's just because there's a 0 there, right? Is it going to always mean that c is equal to 0? Things, right? So meaning your velocity function, 18t squared plus 12t plus 16. Right. I need to go ahead and integrate this. All right. Again, I went from acceleration. I integrated to give me velocity. And you got to take these step by steps. Right. You cannot take one big jump from acceleration to position. All right, I'm going to go ahead and integrate velocity to give me position. All right, so my position function will then be 18t cubed over 3 plus 12t squared over 2 plus 16t plus c. All right, plus c. All right, so when you simplify this function, this gives me 6t cubed plus 6t squared plus 6t. That's a lot of 6's, right? So this is the function I would want to save. I'm told that whenever position is 2, time is 0. So this is S of 0 is equal to 6 times 0 cubed plus 6 times 0 squared plus 16 times 0 plus C. And I know what S of 0 is. That is 2. So 2 is equal to 0 plus 0 plus 0 plus C. Therefore, meaning the C value for this part is 2. All right, as you're going through these, all right, or if you're looking at other videos, if you're dealing with one, the more constant, they may refer to one as C1 and the other one as C2, C3, and so forth, right? So in other words, my position function is 6t cubed plus 6t squared plus 16t plus 2. Wow, all right. Meaning, all right, meaning if you want to go ahead and find the position at time equals 15, all right, you would go ahead and plug in 15 into this function, all right, and you'd find out what it gives you, all right. Just to make sure we are good here, let's go ahead and plug 15 into there. All right, nice, and I get my position, all right, is 21842. Very, very, very nice. All right. We have another problem here. You are told that a stone is thrown straight up from the edge of a roof, all right, where you are 975 feet above the ground, all right, at a speed of 14 feet per second. Remembering that the acceleration due to gravity is negative 32 feet per second squared, how high is the stone 6 seconds later? All right. Again, we're going to use the same function, the same formula that we used before. All right. Seeing what is given to me here, I know my initial position was 975 feet above the ground. My initial velocity, all right, was 14 feet per second. Acceleration was negative 32 feet per second squared. And again, my time difference, right? My delta time, which is final minus initial, all right? T final minus T initial. The final time was 6 seconds. The initial time was 0, all right? Which is just 6, right? Total 6 seconds. And I need to find how high. I need to find S of T. I need to find my final position, all right? Let's go ahead and use this, the first formula, right? I have, right, the first formula is up there. Initial position is 975 plus initial velocity, which is 14 times 6 seconds plus 1 over 2 times acceleration, which is negative 32 times, right, there we go, time squared. Right, so hey, the good thing about this is that I don't need to solve for something else. I can just go ahead and plug and continue, right? Let me go ahead and apply this. This here should be 14. All right, it's 14, 16 times 36. All right, this gave me 483 feet. This here gave me 483 feet. All right, so this is my answer for A. What time does the stone hit the ground, right? At what time does the stone hit the ground? All right, so let's see here. What do we know? At what time does the stone hit the ground? All right, so whenever a stone hits the ground, you know that your height is 0, all right? And that your final velocity is 0 as well, all right? So for B, you're going to want to go ahead and use this second formula, right? Where your final velocity is equal to your initial velocity plus acceleration times time, right? Right, so actually for this one, we're going to go ahead and take a shortcut instead of using this one, all right? I'll come back to this one. All right, so for B, what is your height whenever what is your height whenever something hits the ground? 0, right? So in other words, your x function is 0, right? If you hit the ground, right? If you hit the ground, I knew my initial position, right? That was 975. I knew my initial velocity, which is 14, and I'm looking for time, right? So in other words, I'm going to go ahead and plug it again into the second formula, because this time I'm looking for a different variable. We go ahead and plug all that in. I get 0 is equal to 975 plus 14 delta t plus 1 over 2. Oh, my acceleration, right? My acceleration is negative 32 delta t squared, right? You can use delta t or just t, right? So when I polish this up, right, this is delta t squared minus 16 delta t squared plus 14 delta t plus 975 is equal to 0. Does this ring a bell? Does this ring a bell? Right? Does it ring a bell? What do you think? I'm giving, right? What do you think? Yeah, you've seen this before, right? This is, right? Right? Yeah, you can apply the quadratic formula, right? So x is equals to negative b plus square root b squared minus 4ac all over 2a, right? You'd find out that your a is negative 16, your b is 14, your c equals 975. Go ahead and plug that in, and you're going to get two values, right? Right, this is algebra. We know how to do this, right? One of your x values is going to be 8.26, and the other, right, x values is going to be negative 7.38. But we're not dealing with x, we're dealing with time. You said time. Right, so which one can you use and which one can you not use, and why? Yeah, can I use that one, right? Can I use that one? You can only use positive time. So this here would be the time function, right? At this given time, the ball hits the ground, right? Now the last part is, what is the velocity when a stone hits the ground? There's a few things you know when the stone hits the ground, right? You now know time at that given point, right? You know the position is equal to 0, right? So you want to go ahead and use this function here, right? This function here states that you can tell this function here does not depend on position, right? You don't need position for this function, right? As long as you have initial velocity, your acceleration, and your time, you can find the final velocity, or vice versa, right? If you have the final velocity, I can tell you what initial velocity is, right? So in other words, for C here, right, final velocity is equal to initial velocity plus a times t. Your final velocity is, my initial velocity was 14, right? 14 plus a, which was negative 32 times time, which is 8.26. Right, you go ahead and plug all that in. 14 minus 32 times 8.26. This gives me approximately, all right, negative 250.32 feet per second. Right, and that is it. We are done. Right, so these problems are very physics based, physics heavy, right? We've already been introduced to 2 of these formulas, right? I'm wondering, these are the only ones I would really use. You know, these are the only really three of physics formulas we'd be using, right? Related to kinematics, right? Deriving, and so forth. So we already introduced to the first two. The third one would be a function that is not dependent on time, right? You only need position and acceleration and in a type of velocity. You don't need time to find either or, right? You're told a stone, right? Give me 1 second here. Go back to my notes. There you go. All right, very, very nice. You're told that a stone is dropped from the edge of a roof and hits the ground with a velocity of -125, right? So that is my final velocity. All right, this is feet. And how high is the roof? All right. Wow. All right. How high is the roof? Right. What am I told? All right. The stone is roughly hits the ground with a velocity of 175 per second. All right. Actually, I know what this is. All right. The acceleration. All right. The acceleration is 32 feet per second squared. All right. Go ahead and clear this up. I'm sorry. Awesome. Okay. So the acceleration is 32 feet, right? 32 feet per second squared. The velocity, right, it was a negative 125 feet per second, right? So one thing you would have to ask yourself, is this initial velocity or is this final velocity, and why, right? Right, this here would be final velocity, right? This here would be final velocity, meaning, right, if you're holding to a stone on the roof, that would state that your initial velocity is what? 0, right? Very nice, all right, that is 0. Right? Meaning that, hey, you're asked for position and solve it, right, with our third kinematic equation, right? Meaning, plugging everything in, this would be negative 125 squared is equal to my initial velocity, which is 0 squared, plus 2 times, right, 32 times s, right? So then this here ends up giving me, what does that end up giving me? Give me 1 second here. Right, so 125 squared gives me 625 is equal to 2 times 32. That gives me 64 times s, right? Right, to hurry up before this thing decides to die on me. My pen is dying. So this is, right, I go ahead and divide both sides by 64. So I have 156.25 divided by 64. All right, my position is approximately 244.14. All right. So this here states that that was my initial height. All right, that was the height where I decided to drop the stone from. Right, so this could mean that you're like at a building like that. So, and we see here the importance of this function, right? By just giving the final velocity and pretty much giving the initial velocity, right, and the acceleration constant, which is just the gravity, right, which is just gravity. You're able to find the position, and this is great, right? Great. If you were to go ahead and do these labs in your university physics course, right, you'd be doing things like these, right? You'd have a stopwatch. you'd find ways to like, yeah, it's a very, very, very beautiful, interesting class. All right. So let's go ahead and move on to the next one. Oh, that's it. That's it. Yeah, that's it. Right. So this is going to be our last physics one. All right. The majority of this section was antiderivatives, right? That is the key parts in the remainder of the class and moving forward, and specifically if you're dealing with, all right, Cal 2, Cal 3 differential equations, right? And of course, if you have any questions, please let me know, right? And I'll be more than happy to help you. And thank you very much for, there we go. Right? Thank you very much for your time, and I hope you enjoy the rest of your night. Thank you.